All righty. Okay. Many apologies for the internet here. Um, so where was I? I was talking about the filters, and we have in the center of the field of view, which sees the whole primary mirror, but at a there's a mix of angles from, I should know what they are, let's say 15 to 20 degrees. It's coming in kind of steeply. But at the edges of the field, outside of that center region, you get some partial vignetting. And then at the very corners, it falls off rapidly.
The video feed appears to be back, but no audio.
Video from Pima, but no screen share.
I don't want to. How do I not?
Audio appears fixed.
Yeah. Oops. Trying again. Can you hear me?
Yes.
Okay, great. Thanks. So the radial dependence in the R filter is about 1% chromatically. This is the chromatic term again. And there is a little bit of azimuthal dependence as well. And each of the filters is its own special thing. So I'm just going to skip over the collimated beam projector. That is something that Alana will be doing. And this is where it sits. That's my own picture of it. And then, so what FGCM does, that slide disappeared, I apologize. It is a forward model. So it uses the instrument model that we know from all of our scans. It uses a parameterized atmosphere model. And then it uses a set of 1 atmosphere per night that's allowed to evolve over the night, and grinds and solves until all the photometric observations match together. And what photometric means is consistent with an atmosphere model with no additional gray extinction. And because the fit has basically no gray terms, everything has to be forward, from the top of the atmosphere in, depending on where the telescope is pointed. It's very robust, and this is results from 6 years of dark energy survey, and this is compared to Gaia G-band. So this is summing up DS Grizz into something like the Gaia broad G-band. And it's consistent at the 2 millimag level overall in terms of uniformity, and repeatability at the 3 to 4 millimag level. Something was going on in the corner. You can talk to me about that later if you have ideas. And a lot of the features here, you can actually see the Gaia bandpass. This is from GDR3. Oh, this is HSC is 3 to 4 millimags right there from PDR2. So this was the whirlwind tour of what FGCM is fitting and how it's done in the past. But what you don't care about that. You care, how is it going on with data now? And oh, this is an old picture of me. If you can name the observatory, I'll buy you a beer. I was looking for something on my computer. This is this is what I look like now at LSST. That previous one was from 2004, I believe. But name the observatory, anybody. So what I have done with FGCM so far, I haven't turned it on for our regular data release processing, but I have run it to commission all the software on the dense tethered star field that Yusra was talking about. We had in May one beautiful night of UGRIZ observations and a separate night of IZY. We have a new run that has all the detectors, including those two that were turned off at the time with the new sequencer that I have not processed yet since I'm working on this. Actually, what we have right here is this is not what I meant to put on here, but forget the side right panel. This got miscopied. The left panel is the illumination correction as derived from FGCM. This is the difference between the flat field from the flat field system and the response to focused light through the stars. And you can see there's a very large gradient. The amplitude, which you can't see, is it goes from minus 160 to 160 millimags. So this is imparted by the flat field system, and this has been very annoying because the fitter just has to grind and grind to get rid of it. The gradients are particularly annoying, and so I've been spending a lot of my time working with Alana, working with Parker, working with others on how best to remove that gradient from the flat field. And if you look at images coming in, you can see it in the background and all of that. So chromaticity is another thing that we can do with FGCM. And the model itself is based on the instrument scans. But you can also look at the stars. You can look at the stars and see how they're responding, the chromatic residuals. And that is the left, what the labeled as R1. This is the retrieved star chromatic response due to stars. And the middle is the model that this is the forward model that comes from the preliminary instrument scans that we have from the lab. And here's the residual. And you can see those two look very close to each other. But on the right, there are residuals. It's less than 1%, but there's a couple raft scale things. Those are systematics in the instrumental scan. But what you cannot do and say, oh, I'm just going to use those star color response. That's the old school way of doing it. The problem is that we've got broadband, and if you see a difference between what you expect and what you have, you can just do a color term, which how do you apply that to your supernova or your galaxy? Or you could think, what if I want to go backwards to the instrumental response? But you don't know if it's a problem that you messed up the blue edge of the filter, messed up the red edge of the filter, messed up the detector QE. So those are all completely degenerate when it comes to the stars. So, but what this is a null test. So you can see, did I do it right? but then you can see not quite. We're doing pretty good so far. We're working on making it better, but you can't go backwards. You can use this as a null test. And if this comes out super flat, then I would feel confident that we could apply these then to our galaxies, to our supernovae, to your favorite object of choice, your quasar. In the G band, we have on the left the same. Again, it's pretty good, but in the residuals, these are now still 1.5% chromatic residuals. There looks to be a radial thing going on. So I think that the Materion scans are either systematically incorrect or the way we interpolated them is not quite right. I'm not sure. But radially really points to something with the filter, not something with the detector throughputs. And we have the CBP also for measuring the filter throughputs, but that's a more challenging analysis that is not going to be done on the next next month time scale. But the QE analysis from the CBP is very close. So we have photometric repeatability. Now this is internal using all of the, we know approximately what main sequence star SEDs look like. So it basically does the integrals, does some shortcuts. And we have this is 10% of the stars are reserved. This is the repeatability for the 10% reserved stars. In the upper left of each panel, we have all of the stars. In the upper right, we have the 25% bluest, middle 50%, and 25% reddest stars. I'm just showing R and I here. And this is with signal to noise 100 as the selection. My next run is going to boost that because the width of this is totally consistent with the photometric errors. So, and we have plenty of stars in this field. It's a very dense star, as Yusra was saying. It's one of my bits of code was not expecting 250,000 good quality observations in a single visit. For this is only for the dense field targeted. Do I use everything? The normal FGCM modeling down samples in the dense regions to make sure that they don't overwhelm the statistics and make everything run faster. But when you really want to see what's going on, I have a ton of other plots elsewhere that, maps over each detector, background problems, all of this. So I showed highlights the other day at the DM session, but there are some things that questions that we have not answered, and people might have. What do we do about the standard passband? We can choose a standard atmosphere, that's fine. You want to choose something that minimizes all the corrections, but looking back, we've got, especially, let's look at this one, or doesn't matter. For G, we've got very different passbands radially, E2V versus ITL. Do you take the focal plane average? Do you say, no, take the center of the focal plane, do the E2V average? I don't know if anyone has any opinions. There's Chris probably does. Haven't made that decision. So the other thing is that within the FGCM fit, we have the advantage of knowing we're dealing with stars and all of this. We have not propagated this forward, first of all, into our official metrics. There's work that needs to be done to have the colors in there that I need to talk to Jeff about in more detail. And always on our roadmap has been, how do we make these corrections available to users? Right now, and were these products released as part of DP1? And now I don't know. They should have been. I don't think they were, but they could be. So in the Butler goes an atmosphere for every visit. And in the Butler, you can get the detector throughputs that we have that goes into the model. And you can multiply all those together and do the integrals to your heart's content to do the corrections on your object. But that is not quite scalable, nor is it user friendly. And we have not worked out the interface, and some people here might have opinions on this. Now, some of it is just brute force. It's not even that hard of an integral. If you just do a fast sum, you don't even do trapezoid rule, and you do that. The errors on any sort of source that I've looked at are below 1/10 of a millimag if you do that. I don't know if anyone here trusts any of this to better than 1/10 of a millimag. I think the integral errors are not dominant. And by the way, there's a sitcom tech note 086, which has more details, not about the performance, but about the theory and everything going on and how we're dealing with flat fields. And this is a live document and will be updated with that. But again, that's more the theory in the background and the math, not the performance, which will be in separate papers like the DP1 paper. Chuck. I'm done. Yes.
Really cool stuff. I mean, I remember my early days with doing CCD photometry, and the discussion was around the difference between 5% and 1%. Now we're talking about millimags. It's really awesome. Well done. The radial gradients in the filters. I want to throw something out for you as another. I think there's real signal there, technical signal that needs to be resolved. Because I don't recall the Materion scans having the radial gradient in them when we accepted the filters. So
They did.
At this level.
Yes.
Okay.
These are I looked at when Steve Ritz gave me the raw Materion data before it was even munged by Andy Rasmussen, and he did a better job. He saved me the work of doing a lot of this.
But just to complete your range of, or your list of possible contributors to radial gradients in the filter would be if there is something subtle in the optics of the telescope camera such that the design which made the filter, the front surface of the filter, telecentric is being violated somehow, so that the telecentricity that was designed into the optics is not being realized in the as-built optics. So the telecentricity should mean that there should not be a radial dependence on the wavelength shift through a dichroic filter if the dichroic filter are uniform.
Yeah.
So what? So we could talk offline, Eli. I would love to, because given the millimag offsets that you are seeing, one thing we could do is, under the premise that it is non-telecentricity, if that's a word, is calculate how far we would have to deviate from the optical system being not telecentric to reproduce this radial gradient, and see if that is even plausible.
So I don't think it. So this right here was me taking the material, the Excel file from Materion, and interpolating and averaging over the angles that are incident at everything. And this is what I got. And this is very close to what we see on Sky.
Okay.
So this is the prediction.
Okay.
Before this is actually, I put in a talk 2 years ago.
Okay, well then my memory is now corrected, because I don't recall when we did the acceptance of.
What was measured, what I could plot this as lambda effective or something, which doesn't quite do the same thing. But if you look at like Steve Ritz acceptance summary slides, there's a little.
Okay. All right.
Yeah.
Cool. Thank you.
I'll come to you next. So Eli, when you did that calculation, did you include the vignetting that clips the rays in so that it?
Yeah, that's why it suddenly falls off like a cliff at the edges. That's what. Oh my God. That's the blue where it goes to the other color. That's where the filter vignetting starts cutting in.
About the illumination correction gradients. What are you comparing against what to drive that?
Oh, so what is this? So what first of all, I want to say you see this gradient when you look at the flat itself. Okay, you can that's what I'm working on right now. You measure, you're like, oh, I don't think there should be a 10% gradient across it. The other thing is that so for the dense dithered star field, we had, for example, we had about 30 G observations dithered around with rotational and translational dithers. And this is the solution for what must be going on to get everything to look the same. So this is yeah, and so I look at this and it looks like the flat field. I'm like, okay, we need to fix the flat fields rather than, grinding on it. I mean, we can fix it that way, but I'd rather fix the flat fields because it makes everything easier. Yeah, I don't know if Alana is going to cover this, but yeah, it's a hard problem.
Just in regards to the thing where you asked if people had opinions about it, I wonder if you could, if we have time to ask the science collaborations whether, having nominal filters that correspond to the center of the field or the average of the two different types of detectors and so forth. I would sort of like encourage you to reach out.
So that's why I'm talking about it here. And I'm assuming that anyone from any science collaboration who cares about photometric calibration is here in this room or online or skipped out early. I'm looking at you, Robert Lupton.
Our task is to bring this back to our science collaborations and ask.
Yeah, if you have opinions about it.
Request in any way to the chair.
Yeah. I mean, it's in some sense, it's a mathematical thing. It's, if you fit a line, you want to put the pivot as close to the middle as possible so that errors are independent on the, not too much covariance is there.
Can you sort of give us the wording of what say two options are?
I mean,
like verbally, but it's already fading in my mind, right?
Yeah. Oh, the standard band pass. Would you prefer it as a focal plane average, so it looks like nothing in the focal plane, or the focal plane center, so it looks like the nominal filter in E2V, but that means that there's increased corrections from the edges in ITL?
So I have a related sort of meta question. What do you even mean then by standard, right? Like, is this like the one that everyone says when they say Rubin R? But that doesn't actually mean anything then. So like maybe you need to abandon the very idea.
Oh, no. But if you read the FGCM paper or the sitcom tech note, it's standard is when we quote our photometry, this is our reference bandpass. And you could, we are standardizing to that system. And so then you can trust that like our coads and everything are using that system. But it is two telescopes in one.
Just a minor factor that might go into that decision. When DM is doing the coads, will they be doing anything to compensate for the differences in filters at the time of the coad?
Right. So that's a very good question. The answer is to first the multiple parts of this. If you choose your standard wisely and you do your coads and you do the calibrations correctly, the more observations you put into the coad, the more it converges to that middle. And we are going to be at that fairly quickly at the efficiency of LSST. But at the same time, we do have the ability to basically coad the transmission curves of everything that went in to the coad, in the same way we coad the PSFs, to know what that is, for the coad, with the right weighting and everything. We have not done that yet because to do that with our standard coads is a complete nightmare of amount of data that you have to have. But we're moving to these so-called cell-based coads where each small cell is, coadded consistently. And so each cell will have its coadded transmission curve attached to it. That will be in place for DP2, but not DP1. Yes.
So you've described a really interesting process to collapse a 12-band survey into a 6-band survey, right?
More with the radial effects, it's
So-
12 plus. Yes.
But you could turn it around and say, actually, that's a plus. It's a feature, right? And that actually the QE difference between E2V and ITL gives us just a little bit of extra additional spectral resolution that we could in fact exploit. So that would suggest a data product that exploits the difference between them rather than trying to homogenize them. Have you thought about
that? Someone is welcome to work on that. Everyone who has tried that kind of thing in the past has left the field.
I have a question from Zoom.
Yeah, Lynn, can you ask?
Oh, thank you. I was gonna say I kind of have an opinion on the standard passband. Just because we do use the standard passband for so much about like describing Rubin and describing its like expected magnitude limits. I would love it if you came up with something that basically expressed what's the sort of expected average throughput. And I understand that it'll be different in different parts of the chips, different parts of the focal plane. We actually do have a notebook that like quantifies this for some kinds of SEDs in the syseng throughputs repo. But yeah, I think we do need a standard passband that we can talk about, so we can say, oh, it's Rubin R band, and probably.
So I mean, it'll come out in the wash in the end. I mean, there's a absolute calibration term and flat field normalizations. These are all the. But your vote, I hear, is you would prefer focal plane average. You like that better because it's more what OpSim kind of expects. Is that?
Yeah, and I think when you're trying, I think you're right. When you're looking at it in a particular visit, where did a particular object land? You have a different problem. But when you're saying, hey, what do I expect to get from Rubin? You're saying like, what's the average over the focal plane?
That's the argument for average of the focal plane. It's kind of the split the baby. It's neither A nor B. That's probably what I will end up doing. That's what my code does at the moment. But.
Yeah, and I think it's not even necessarily as because most of the area is E2V, and that's where like at the edges so you don't have that much vignetting, but you have a little bit, and there's other things that are yeah, anyway. Yeah, I think that would be great. I'm glad that's the way you're thinking you might go.
All right. But I will do average excluding the corner detectors.
Okay, I think we should move on. Let's thank Eli again. We should have time later for more discussion, I think, but let's move on to Ilana.
So sorry, I completely forgot that I said I was going to talk about the flat field system, but I added one slide really quickly. So we do have a working flat field screen. We have 2 LEDs for every band, total of 12 LEDs with the exception of the U band. And we use those for our white light flats. You can see pictures of both our visible and combination of our visible LEDs. I do think that it is probably true that that gradient that you see on the flat field screen is what causes the gradient because of scattered light. I think we have single bounce scattered light paths in our system that go directly onto the focal plane. And I think that is the gradient that we see. That's my best guess today. We do have to do some modeling to confirm that. Anyways, and we also have monochromatic flats with our flat field screen using a tunable laser. We can do 1 nanometer steps, and we have confirmed that we have enough laser light to take data for every filter except the U band. There may be some fixes we can do so that we also get U band light, but right now, that's where we are. Yes, Eli. I band is also a little bit, yeah, our tunable laser light drops off in the middle of the I band, or really on the blue edge of the I band, so it also is tricky there. But for the other ones, it's okay. So, okay, now switching over to the collimated beam projector, I'm gonna give an introduction to the collimated beam projector, talk about uses of the CBP, how we calibrate the CBP, really like who calibrates the calibrator, and then give a kind of quick status of measurements with the CBP and our next steps. So the idea with the collimated beam projector is that if we can make an artificial star, we could know its magnitude or its brightness and its color, and thus it can be a good calibration source. And one way to make an artificial star is to invert a telescope, because telescopes take collimated parallel beams of light coming in at different angles. They convert those into position on the focal plane. And so what we can do is we can make spots of light on the focal plane of a telescope and project those like starlight anywhere using our telescope. So here's our collimated beam projector for Rubin. We have a tunable laser. So the telescope is a Schmidt reflector telescope. We have a tunable laser light fed through a fiber into an integrating sphere. And then the integrating sphere keeps the laser illumination unpolarized and uniform over the CBP focal plane. Then a photodiode that comes out of the, a photodiode in the integrating sphere lets you measure the number of electrons going into the CBP and thus into your telescope if you know the CBP transmission. So that's the idea there. We also have 5 masks that can be exchanged at the focal plane of the CBP, allowing us to project different patterns onto LSSTK. Here's the CBP on the dome. As you can see, we can co-point the CBP and the telescope so that we can point at any different part of the mirror and at any different angle. And the idea here is that because we have a tunable laser, we can really measure the wavelength dependent throughput of collimated light. We can look for reflectance and transmission variations across the mirrors and filters, measure QE variations across the detectors, measure crosstalk nonlinearity because we can project individual spots. And then of course we can study ghosting in stray light, study bending modes for AOS, other things that are not really related to calibration. So how do we calibrate the CBP? What we use is we have a calibrated light bucket. We have a lens that focuses light onto a NIST calibrated photodiode. We calibrated the lens also using NIST photodiodes. And so this is what we are using, what we've used. And basically the idea is that you send bursts, we send bursts of laser light from the CBP onto this light bucket. And we have, we basically measure a charge accumulation with photodiodes on both ends. So basically in the integrating sphere before it goes through the CBP and then at the other end. And this is how we calibrate our CBP transmission. And so for our results, we've measured the CBP transmission twice, once in April 2024 in Tucson and once in November 2024 in Chile after it had been completely destroyed and then rebuilt. And you can see that they are chromatically very different from each other. I will note that the data that was taken in Chile. So here you can see the function of wavelength, what the CBP transmission is. I will note that the data in Chile was taken in a very hot laser room because we just didn't have cooling. So that's the situation right now. So now I want to talk about the status of the measurements with the CBP. So for ComCam, here's a grad student, Nathan Amaru, who has been doing a lot of the analysis of the photometry of the CBP spots. But we took CBP spot measurements for all 9 detectors in ComCam. And at the time, we did not have the electrometer working. So we just turned the laser on and took data with the laser in continuous mode with the filters. And then we took the filter off and we just took the ratio of the flux in the 2 spots. And from this, we have both G band and R band measurements. And we are going to be putting these in a Git repo so that everyone has access to them. And you can see very clearly our ComCam G band red leak, which is very strong. Then for LSST-CAM, you can see a GIF of our R band, one of our R band filter sweeps, as we essentially have, oh, shoot. GIF only plays once, I guess. Okay. But basically the idea is we have a mask where we can project a single spot onto each detector. And then we can sweep through laser wavelengths with this mask. And this mask is projecting spots that are about 160 pixels across each detector. And so we have successfully done these sweeps at multiple different co-pointings of the CBP and the telescope for most of the filters, and also for no filter in the beam. And the idea here is that the no filter in the beam is easiest to analyze, and it gives us information about detector to detector QE variation. So this is where we're starting for our initial measurements. And so kind of here are some of our initial results. We can see very clear variation in telescope response for different CCD types. On the left, you see E2V, and on the right is ITL. Now, I will say these are done with the CBP transmission curve from Tucson. The one that is from Chile just, yeah, is garbage. So I wish that were not the case, but that's where we are right now. But you can clearly see variations across the detector. And with this data, even if we're maybe not 100% certain that we trust the CBP transmission curve, we can get ratios and differences across the detector, across the detectors on the focal plane. So for the next steps, in the coming months, we're going to install the CBP calibration system and redo the measurements of the CBP itself. We'll also have fiber spectrograph data for our laser, which will help us trust the results that we see here. And there's plenty of analysis in addition to this hardware. We're in the process of doing analysis. And I think the next kind of fun problem is going to be figuring out how we're going to do pupil stitching, how we're going to take all of these co-pointings with all of these different filters and make it into one uniform filter passband. So that's all. Thank you.
Did we have questions for Ilana?
You showed a picture that I should have, if you go back to the previous slide, that the different colors on the focal plane is basically the G-band QE of the camera. And Aaron Rudman did some nice analysis of integrating the QEs according to how our eyes respond, and it looks just like that.
I mean,
in terms of the color, that's what I was showing, the colors, yeah. But I didn't show the focal plane. Yeah. And HSC and DCAM, all the cameras with multi, you can see especially the G band where our eyes are sensitive.
Any other question? Yeah. Great.
Hey, thanks for this. And I was really glad to see, you're putting the ComCam data on GitHub for all to see. Is the intent to do that also with LSST-CAM, including all these like detector by detector possible variations?
Absolutely. Well, maybe in the Butler, maybe in a GitHub repo. That we haven't decided, but we will do the GitHub repo for ComCam very soon, this coming week. Yeah, right, you should answer.
For LSST cam, those will be official data products released as part of the data release, but this is just a side thing, heroically done at the end of the, ComCam. So we're just getting it out there sometime.
Yeah, just a brief comment. So we learned a lesson in a previous century trying to do wide field survey on the Blanco. And that is that the night sky, so we want to look at objects that are very faint compared to the night sky. So getting a flat field for the comparatively brighter night sky is an imperative, and that's what we've been talking about. The color of the night sky is strange. And what we had to do was to go to Kodak and ask them to make a filter for us that had the same color spectral response as our night sky, and then we use that in the old school of projecting onto a screen. With the luxury of having a tunable laser, it seems to me that one could actually imitate the color of the night sky and be rid of this problem.
That is absolutely the plan. I don't know how we're going to do it in U yet because the laser throughput. That is not going to be ready for early, but it will be. We're only last week. When did we first get the monochromatic flats working?
Yeah, it's within the last, I can't keep track of
But
time,
anyway,
within the
that is
last
the
week or so.
plan. But at the moment, we actually have 2 LEDs per filter, and we can do a first order correction, and that's our first plan.
Any further questions? All right, if not, let's thank Ilana again. I think, Chris, you're up next.
Yeah, I'm also pulling up my slides.
Okay, so next up we have Chris Stubbs.
All right. So just a couple of quick opening thoughts. This has been a great meeting. After spending forever trying to get this thing working, just congratulations to everyone, both people who built it and people who are doing science. I think I'm kind of a grumpy guy, but I'm actually happy. So it's great. Furthermore, we have phenomenal colleagues, Eli and Ilana, who I am absolutely convinced are going to nail all the problems just described about instrumental throughput and its challenges. And so let me talk about the other part of the problem, and that is that every time we take a picture from Rubin, we're taking it through a time variable optical filter, which we happen to breathe on a daily basis. So here's the throughput of the Earth's atmosphere. Pieces of it are quite deterministic. The Rayleigh scattering from nitrogen and oxygen and the deep oxygen absorption features there at about 760 nanometers. Those depend purely on barometric pressure. So that's quite predictable. The parts that are less predictable are clouds. Well, we just are going to banish clouds from the summit, so that'll be easy. But water vapor, which are these sharp molecular absorption features, if you look at that at really high resolution, those lines are absolutely saturated. There's no transmission through the atmosphere at the H2O lines. And there are aerosols, which are particles that have size distribution comparable to the wavelengths in question. So in this nasty Mie scattering regime, where the wavelength dependence of the continuum scattering depends on the size and the shape distribution of aerosols. Okay, so in anticipation of this being a problem, something like 25 years ago, some of us wrote into the project plan a dedicated telescope to go and measure the optical transmission of the atmosphere. This is not first with us. The Sloan Digital Sky Survey had a photometric monitoring telescope that never gave any useful data. DES had photometric monitoring auxiliary instrumentation that was not actually used in the photometric calibration. So let's try it again, right? That's the plan. So there is this dedicated 1.2 meter telescope that has already served as a really valuable path breaker for system integration for the project. If it did nothing else, it saved us an immense amount of time in the commissioning of the overall system. because it ran with the scheduler, same detector, same readout system, same data processing. But its real plan, its real goal in life was to measure the optical transmission of the atmosphere with a spectrograph that uses stars to backlight the atmosphere. So there are two different disperser and filter combinations in place in the auxiliary telescope. One shown on the left is a holographic disperser. So this is a very slow F18 beam. There's no slit. You just put a grating in the beam and you measure the dispersed light. So on the bottom left, you see the undispersed 0th order image of the star, and the streak up going vertically is the first and slight second order superimposed spectrum of the star. Is the principle clear? I'm looking for affirmation. Is the principle clear? Excellent. On the right-hand side is a slightly more constrained version of the same thing, where we stick in the beam a filter whose optical transmission function looks like the thing in the bottom right. So you get a chopped up version of the spectrum. And boy, does that make life easier, because you can just do aperture photometry on the thing on the right and get what you want out of it. So there's a really cool tool that, if you don't know about, I'll advertise, that NASA supports, which lets you input a handful of parameters: how much ozone, how much water vapor, how much barometric pressure, what zenith angle. So a handful of parameters, like maybe this many parameters, and it delivers a high spectral resolution transmission spectrum of the atmosphere. So to Eli's point, our goal here is to assign to every Rubin observation a handful of atmospheric characterization parameters derived from Oxtel, run it through a tool like this, and be able to deliver the relevant atmospheric transmission function through which we are observing. So I'll describe quickly the analysis that's happened to look at aerosols and water vapor. So these quad notch measurements allow us to basically just take I think this picture is probably better. So on the left-hand side, you see the spectrum, and ESCA has written some code that just chops it up into boxes, and you add up the flux after doing sky subtraction, and that gives you basically 4 simultaneously observed spectral elements all through the same shutter, through the same air mass, okay? So it's a pretty straightforward extraction process. The curve on the left shows you what kind of air mass coverage we're currently getting over Oxtel, basically taking star from the horizon up to the zenith, wide range of air mass. And the curve on the right is basically taking those aperture photometry values and asking, in one band versus another band, how much excess extinction is there as a function of air mass? Okay, so it's essentially a color air mass term in Abi's language. And this is really quite beautiful, right? That's a pretty good Bouguer curve extinction fit. And furthermore, that's not just one amplifier, but we take the spectrum and displace it onto 3 different amplifiers at every visit, and that's 3 of them all sitting on top of each other. So we can do a really good job of extrapolating to the color of the star above the atmosphere. And if we know that, then all we need is one apparition at a given air mass to deduce what the atmosphere is doing at that particular instant, okay? So that's worked actually quite well. And my colleague Eska Peterson has a paper that we've been on the verge of submitting now for months, but it might actually happen sometime soon, where we do a joint fit to that atmospheric data to gray extinction that is wavelength independent, and then a parametric description, which is the kind of industry standard for aerosols, which contains a strength term, which is this K that sits in front, and there's an exponent alpha that describes the wavelength dependence of the scattering. And these 3 plots show you on the top, as a function of image sequence number, the attenuation at 500 nanometers in magnitudes per air mass, which ranges from some canonical value up to many tenths of a magnitude per air mass. We get clouds of dust blowing over every so often. The plot in the middle is the fitted angstrom exponent, and the thing on the bottom is the gray extinction term. Okay, so we do a pretty good job, and for the first time in my life, I think have moderately credible measurements of the wavelength-dependent scattering of aerosols, which is actually quite an accomplishment. Shifting to water vapor, our friends in France have been expending a lot of effort in extracting the equivalent width and strength of the water vapor component, and this just shows over a multi-year campaign that the precipitable water vapor in millimeters, which is basically take all the water in the atmospheric column above the observatory, condense it, get out a ruler and measure how deep it is. So we have a few millimeters of effective liquid water over our heads, and it ranges by almost a factor of 10 over the course of seasons and nights. So the interesting question becomes, what is the angular and temporal correlation function of these variable components of the atmosphere? Right? That's what we need to know in order to compensate Rubin data. Do we need to follow the Rubin telescope at every single pointing, or is it enough to just make a broad model? So we've made some good progress in measuring that. So back-to-back measurements separated by a few minutes to see how repeatable can we measure the water vapor. The answer is to better than a millimeter of being able to measure the water vapor content. And if you ask, if I take a measurement at time t and a measurement at time delta t later, how much does the water vapor change as a function of that lag? So that's what this plot is. The horizontal axis is delta t between measurements, and the vertical axis is delta precipitable water vapor. So you can sort of see the coherence time, the correlation time for water over your head is typically on the scale of hours. What about the angular variation of water vapor? What if you look at this star over here and that star over there? Does the precipitable water vapor depend very much on the angular separation? And the short answer is no. Most of the time, the water vapor burden above the observatory is just a number, but it changes as different parts of the atmosphere blow past the observatory. So my summary of what we've learned here is, number one, Auxtel's been a really good system integration pathfinder for the whole project. The combination of the telescope and the instrument, I'm going to say, can perform reliable measurements of the variable and important aspects of atmospheric transmission. We can usually assume a spatially uniform distribution of water vapor and aerosols over the observatory, but that it varies over time. So why is that? Well, partly because most of the water in the atmosphere is pretty low, and we only look up a range of about 60 degrees of zenith angle. So that means that we're only looking at about a kilometer of slab of atmosphere above the observatory. But that slab kind of blows over and changes over time. So that's meant to be conveyed by this picture over here on the right. I think aerosols are the most difficult and pernicious thing that we face here, because that continuum scattering is very gentle and it's hard to measure. But I think we're on a good track towards figuring that out. So where are we headed? This multi-band filter trick works really quite well, and I'm hoping that the project will see fit to replace the current filter with a new one that's shown in the top right that'll actually extend the coverage further to the red and let us get a better baseline for the aerosols. And by the way, maybe even the water vapor as well. We're in the process of installing pipeline reduction of the Auxtel data to extract these summary atmospheric parameters. And I'll show you some slides from Michael Woodvasey here in a second about using dual band GPS receivers to measure the water vapor content day and night along various sight lines. And so the goal here, like Eli said, is to be able to attach to every single Rubin visit, not only the instrumental throughput, but also the throughput through the atmosphere that's pertinent to that particular observation. And now, shameless plug, I learned a lot doing this Rubin project, and at some point I took it upon myself to try to write it all down. So there's a book that you can get for free from MIT Press about how to thrive in big projects like this one. And end of shameless plug. So let me go end of show. And yeah. Let me do Michael's, and then we'll do them all together, because I think it's all of a what is this? Whoop, 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 whoop. I've done something terrible. Over here. Thank you. Thank you, Alana. So I'm presenting on behalf of Michael Woodvasey. There was a poster up by Sarah that described this earlier in the week, but basically, here's the deal. The time delay for radio frequencies propagating from a constellation of navigation satellites to the Earth depends on a lot of things. Among the things that it depends on is the water vapor that changes the effective index of refraction. It does that in a wavelength dependent way. So if you have a dual band GPS receiver, you can hope to tweeze out the component of the path delay that is due to water vapor in the atmosphere. So there's a thing called zenith total delay, no, zenith tropospheric delay, which is how much does the atmosphere affect the propagation time of GPS signals. So this shows for a variety of dates at a particular location, this total tropospheric delay in units of meters. Part of it is just oxygen and nitrogen. That part doesn't vary very much. The barometric pressure doesn't change very much. So the majority of the variation that you see here is due to variable water vapor above this particular site. So Michael and his colleagues are in the process of installing this down in Chile. They run the code through, they run the data through sort of industry standard geodesy and meteorology code that delivers this tropospheric delay. You then use local barometric pressure to subtract out the sort of standard dry atmosphere component. And what's left is, you know, histograms of residuals after they do these fits. So the GPS antenna for this is currently installed on the water tower, excuse me, the weather tower, the dim tower adjacent to Augstel. And the fun thing about this particular instantiation, if we get it done right, is that it will measure this tropospheric delay along independent lines of sight to each individual GPS satellite. So you'll be able to look at the azimuth and elevation dependence. So that's a work in progress, and our colleagues are in the midst of installing that, hopefully in the next few weeks. So happy to take any questions people might have.
Chris, I don't know if you can hear me. I'm on a train. This is Morgan. My question is, how would you characterize the importance of aerosols compared to water vapor? Water vapor, you said, was equivalent to 2 to 15 millimeters of water. What would be sort of the equivalent millimeters of water that the, of course, it has a different spectrum that the aerosols would be. I'm just trying to get a sense of the relative importance.
Hi, Morgan. Long time no see. I think the relevant units are how much extinction do we have in magnitudes per air mass. I think that's the right phraseology you put it in. I think the aerosols are much more highly variable than the water vapor. It's hard to get many tenths of a magnitude of extinction from water vapor in clear skies. So I think the aerosol variability part is much larger. And also, the other quick point here is Eli has an absolutely nailed to the wall method to use color dependent residuals in the redder bands to compensate for the water vapor aspects.
Thanks, and thanks for a very interesting talk.
I don't want to interrupt, but when you're done during discussions, I have some extra slides I can show on that.
I can take a hint.
No, I'm not.
Very nice talk. I think it's very important having many, for calibration purposes, having many ways of getting to the calibrations. I know FGCM will can do very well counting sort of water vapor and various other things. And so I think that's it. I think from sort of a calibration engineering standpoint, having multiple cross checks and measurements is very important, like we did with DES, for instance. And I'd also like to note that on our telescope for SDSS was actually instrumental for calibrating the first 7 beta releases of SDSS. And that's all. Thank you.
Yeah, so I completely agree with you, Doug. The scope of my talk was quite narrow, and I thought where you were going, that I'll just complete the thought, is we're going to supplement all of this with the use of spectrophotometric celestial calibrators. And I know a lot of people in this room have been involved in efforts to push the precision frontier of those. And I think having those independent ability to close the loop, I think, is really going to give us a realistic assessment of systematic errors on photometric precision. Speaking of which.
No, so the water vapor absorption features span the spectrum. Well, are all of them optically thick? Do you treat them the same?
Yeah, so the standard lore is that extinction just goes like secant Z, right? But for these water vapor features, that's not true because the marginal increase in absorption is only due to the Lorentzian wings of saturated lines. And so it goes more like square root of air mass. And David and Eli did some really cool joint fits to show that the data are consistent with that. So I think a lot of the lore in astronomical photometry is just completely inapplicable at the millimag level. And yes, they are saturated.
Chris, could you back up a couple of slides showing the dual band result scatter in precipitable water vapor? There was a sort of Gaussian looking distribution.
Maybe.
This is in Michael Woodvesey's presentation.
Help me out, guys. I don't know where web browser went. Safari, maybe? Okay, Safari. Where did it go? Ask your question.
Okay, it's totally not there either.
So this has been done before, attempted, I would say attempted before, without very much success. That is to say, the 10 to 15 millimeters of precipitable water vapor were captured very well. But there was a lot of systematic coming and going error, systematic error down around the 2 millimeter level. And I guess we have to first ask the question, where do we want to be? Okay, and this is going to work.
Yeah, so my answer is that's a legitimate concern.
Sorry, we can't hear the answer on Zoom.
Oh, sorry. I understand your concern, and we decided early on to not include a GPS receiver as part of the calibration suite. But one of the things that changed our mind is Killian Sommer with the Stardust project has done a lot of work that actually shows even at those low PWV values, the results seem to be relatively reliable, okay? And furthermore, it's just dirt cheap, right? It's like a few $100 to get one of these receivers and an antenna. And furthermore, because the project decided to shut down Augstel for some of the early observations, it seemed like a prudent thing to do just to be able to cross-check. So we sort of put a duct tape and bubble gum one there that's operating there currently, soon to be replaced by this other version. And in the spirit of what Doug said, kind of like, why not, right? It's not going to be our primary source, but I think the more we collectively learn about this, the better position we're going to be in to have confidence in our results. So the sort of marginal gain in information per investment here seems particularly good. That's my answer.
So as an astronomer who mostly tries to ignore the atmosphere, I find this all very fascinating. I'm curious more broadly, how much of what you said you think applies to sites other than, Rubin's site, right? Is this stuff where you're going to publish it and it's actually going to be useful to other people? Or is this really like, this is only aerosols right there and you can't believe it anywhere else?
The aerosols are very site specific. And I think one of the reasons why Chilean astronomical sites are reputed to be photometrically good can be attributed to the difference of aerosols between that and volcanic dust blowing around in Hawaii. But that's a supposition on my part.
Yeah, it's very site specific, and actually that's one of the challenges of like using satellite measurements. You say, oh yeah, it's great, it's overhead and it can see everything, but it's integrating, and especially for aerosols, if the cell covers the peak in the valley and someone is burning fire down in the valley, then it's going to measure, yeah, you have tons of aerosols, but not up there. So you kind of have to fit it looking up.
If you've been observing at CTR Pachon, you can see this inversion layer that just gets set up and traps the marine aerosols below you. It's quite site specific.
Anyway, if I could share my screen, I have a little bit more answering a couple questions about water vapor. Let's see, share. And hopefully, this is from slides that I gave to the several years ago, showing the broadband. So here's Z band with no atmosphere. This is nominal from years ago. So now we add a little bit of water, and you add a lot of water, and then you put them on top of each other, and you can see that the water vapor cuts off the red corner of the Z or the blue of the Y band. We're looking at that. And the primary impact is the overall transparency. This is talk about hitting millimag level. What really matters is actually is the chromatic effect, because otherwise it's degenerate with gray. And the size of the impact depends on the SED, and I did this bunch of integrals for stellar SEDs and supernova 1A. This is a desk talk, so I'm biased there. And for I minus Z colors to be consistent at the millimag level, we need to know the PWV at about 1 millimeter with the LSST passbands. So that's answering Tony's question, I hope. Something like that. You don't need to know the water vapor at 0.1 millimeters to do millimag. Yeah, 1 millimeter. And then, so this is something that Robert Lupton asked me about years and years ago with DS. So a little bit of history. We originally were using the GPS that we had at CTIO as an input into the FIT. And it was good most of the time and terrible some of the time. And we actually had a little spot that showed up in why is there a deficit of red galaxies at this one spot in one of our early DS footprints? And it's because the Z band had been shifted so much by erroneous measurements. Now that goes down over time. DS does not have as many overlapping epochs as LSST will, but it was enough at that early time. But what I did here was the default FGCM model is a smooth evolution of the water vapor in the night. That seems to work really well, but you can also do, even with just our puny 60 detectors that we had on DECam, for Z-band observations, just look at how the red and blue stars move relative to each other and back out the water vapor on a visit by visit basis. And we're gonna have, a lot more stars per visit in LSST. And then, so that's the GPS on the y-axis. And it works pretty well. And then there's outliers, and these larger outliers are definitely systematics in the GPS measurement that we had. So I just wanted to show this as how you can use the broadband photometry. And again, there's no air mass term for this. We just ask modtran, and integrate and say what the water vapor. So that takes care of those saturated lines.
Wouldn't ozone affect this kind of analysis as well?
In the Z band, not much.
No, this is just C-band?
This is only Z exposures. Now, one of the things is, how do we know the water vapor when we're measuring in G or R? We don't, and we don't care. Because the water vapor doesn't affect those. So this sort of analysis can only be done in Z and Y, but that's the only place that we care about the water vapor. This is not as simple an analysis to do with the aerosols, because that is a smooth component, and so you don't have this really distinctive notch that comes out.
Were there any other questions or comments? How are we on time? All right. We're basically there. Shall we call it a day. Thank you, everybody. And